Hello everyone and welcome. My name is Liz Pemper and I'll be your moderator for today's WJE webinar. Are your healthcare facility walls and roofs helping or hurting your primary mission? During the next hour, WJE Enclosure experts Kevin Kalata and Bruce Kaskel will discuss tips for identifying problematic conditions as well as strategies for repairing or making these problems more manageable. This presentation is copyrighted by Wist Janney Elster Associates. And now I will turn it over to Bruce to get us started. Bruce?
Thanks, Liz. Okay, so we have a full hour presentation. We'll save some time at the end for Q&A, but we wanted to go over a topic that we believe will be of interest to many people. These are our learning objectives. Please feel free to take a look at them, and we'll go over these in quite a bit of detail as we go through our presentation. So our outline today is to talk about healthcare enclosures, to talk about some of the specific issues that revolve around heat, air, and moisture, movement through walls. We'll give some case studies of those, and then we'll talk about commissioning the enclosure, which is a way to do some proactive steps to help avoid future enclosure problems. So we'll start with an introduction, what makes healthcare enclosures unique and worth consideration. So first and foremost, we have to admit that healthcare takes place inside the facility. The enclosure, being the envelope that protects the inside, is not where your primary mission is occurring. But we understand that your mission of taking care of patients inside is critical, and that the enclosure and its performance really helps or can hinder your primary mission. And to such an effect, we really understand that you need an enclosure that will solve problems or avoid problems for you that may be coming up, that could come up and you don't want to deal with. So healthcare facilities aren't like other buildings. We deal with buildings of all types, and we recognize that healthcare facilities have a lot of unique features. We are mindful of those considerations. You have infection control concerns that no other buildings really have to deal with, and that drives a lot of your environment, of what you deal with on the inside. And the enclosure has a big participation in making sure that that interior environment is working for you. Designers understand this in preparing healthcare facilities. Probably the one we deal with the most that often is not understood as well as it could be is the way air can flow through structures, through the enclosure, and the problems that could occur with considered unwarranted airflow. Kevin will talk about some of those issues in some of our case studies. And healthcare, of course, is governed by a lot of standards today, more and more thicker standards every time they come out. They are constantly evolving. Every state has their own requirements, their own Department of Public Health that's going to inform the healthcare facilities in those areas about what they need. And we obviously have to participate in understanding those and make sure that our enclosures are going to work for those demands. The last bullet, which talks about the goals through the continuity of thermal, air, and moisture barriers, I think the key word that we really want to reinforce today is the word continuity. We've seen a lot of case studies where the design is good, the barrier is good, but a lack of continuity with the smallest of breaches can create a significant problem. So when we talk today, we're going to be talking about these three terms, heat, air, and moisture. And what we really want to make sure you don't neglect in this is that they are all very interrelated. Heat and air and moisture all interact with each other. We have to consider that. As an example, today we design much more airtight buildings than we did in the past. And of course, we find that there's oftentimes moisture problems relating to creating airtight buildings. And one of the reasons for that is that in the past, buildings have had an integral or an unanticipated drying function because the air movement would help dry out mass walls. And today, the airtight walls are inhibiting that drying function and creating a lot of moisture problems. So air tightness, moisture, heat, they all work dependently, and we have to consider those interrelationships. Of course, what we're guarding against, if we don't need to say in too much depth that these are the kind of things you just don't want to happen. You don't want to see water, you don't want to see condensation, you don't want to see corrosion, and you certainly don't want to see organic growth. So I'm going to turn this over to Kevin at this point. He's going to talk about these three aspects, heat, air, and moisture. And he's going to start with the first topic, heat.
All right, thanks, Bruce. We'll start off with some general principles, and we'll talk about how those affect the enclosure, and then get into some case studies to kind of help kind of show some examples of those points. Heat flow, we've got three types. We've got conduction, and we're thinking about our enclosure. That's the materials themselves and how that heat flow is going through the materials. When we talk about convection, we're talking about the heat energy movement through a fluid. And when we're thinking about our enclosure, we're thinking about air spaces and air films. And then there's radiation, and whether that's that's the heat energy through space, and is that either through the solar radiation or maybe a mechanical radiation effect. But heat's going to go from hot to cold, and our job as designers, as enclosure consultants, is to try to help to manage that heat loss for energy savings, as well as for just performance from condensation and other factors. And so we'll talk a little bit about the conductivity of materials and some of the thermal bridging aspects that need to be considered. So here's an example using THERM, which is a heat flow simulation program. It's 2D. It's a very good comparative program. It's based on finite element analysis, and it was developed by Lawrence Berkeley Lab. And it does have some drawbacks as far as three-dimensional and being able to look at air and other things that it can't do. But what it can do is look at things for comparative purposes and give us a help to understand what the temperature patterns and gradients are going to be across wall systems, and help us to predict condensation based on the surface temperatures being at or below a dew point. So for this particular one, we've got the three wall cases, more of your classic or older buildings where you've got an insulation in the stud space. Then we've got a hybrid system in the middle where we've got some continuous insulation, but still insulation within the cavity. And then finally to the right, a continuous insulation system. And as we look at how, with an exterior temperature of 0 degrees and an interior 70, just look at how these walls are behaving and the thermal gradients. And you can see some of the thermal bridging happening at the steel studs, and some of the temperature effects down to even 13 degrees on the back surface of our sheathing. And so it's quite cold. And if we get air into that area, especially humidified air, we have to worry about condensation effects. Just a little bit of continuous insulation in the hybrid system helps us out, warm those up a bit, but we still get some buffering effects by the insulation within the cavity, and so we're still at a little bit lower temperatures on that sheathing than we are as you look at a full continuous insulation system. There you're getting the most bang for your buck, so to speak, for your insulation and the efficiencies and the reduction in potential for condensation. Up in the top corner, I just show, for reference sake, if we had a 70-degree temperature and a 30% RH, which could be somewhat common in a healthcare facility in the wintertime, we're looking at a 37.1 dew point. So you can see on that, the wall section all the way to the left would be a concern. And to kind of illustrate some of those concerns, here are some photos from healthcare facilities where we're in a mechanical floor here where the FSK facer is exposed on the backside of the area, and you can see some water droplets forming from condensation. You can also see some sweating in that middle, the middle photo there, where the column is connected with the steel embed. You can actually see frost down at the bottom there, because that steel is penetrating through the thermal layer and connecting to the cladding system. And then finally on the right, interior finishes removed. This is the back surface of a precast concrete panel, and you can see the frost buildup on that panel. And one way that can be used to look at these heat flow patterns and try to look for anomalies or where there's might be a problem is to use IR, or infrared thermography. We've got a couple photos here of a hospital taken at different times. And you can see in the bottom left one where you've got a lot of heat loss at window areas, but that would be to be expected, right? We've got lower R values there than you would have at your opaque walls. But what I do want to bring your attention to is that upper corner toward the center of that photo. You can see that red kind of whitish area. That's a parapet area where there was that breach and airflow flowing into that parapet, so warm air on a winter day getting to an area where it shouldn't be. And as you look also to the photo on the right, it's a nice comparison of two different wall systems in the same hospital. To the right is the original precast cladding that had a fiberglass bad insulation with FSK facer, and to the left is precast panels with spray foam. You can see the spray foam insulated side is performing much better thermally, a lot less heat loss. We also want to consider the conductivity of the thermal bridging. I know especially designers, when you're looking at meeting energy code, you're thinking about, okay, what kind of insulation am I going to use? As far as am I going to use extruded, expanded, polyiso, where can I get the most R value? But you also want to think about it in your other materials that are also affecting, especially at thermal bridges. Your connections, your clips, or your flashing systems. Look at copper and look how much more conductivity you have in that versus a stainless steel, and how that might affect when it extends past the thermal layer. And so that's something to keep in mind. And then as you look down, is the lower conductivity materials is the insulation, and then polyurethane that's also used for window systems for thermal breaks and what. And so how does this work into our healthcare facility? Well, here's an example of a project that we were looking at replacing a curtain wall system. And we did some thermal modeling similar to the thermal models that we were doing before in those wall sections, the same program. And we were finding that the temperature reading, if you look at the bottom left little snippet there where we're looking at the temperature reading where the glass and the frame come together, we're showing some areas where we had some potentials for some increased condensation just based on the lower temperature reading. So we thought, all right, let's see what we can do with this. And just looking at the spacer for the glass, aluminum is more of the common standard spacer material, but there are also warm edge type spacers. And this, we looked at one with a polyurethane break as well as one with a stainless. And we found by just making that switch alone, we could increase that surface temperature reading there anywhere between 3 and 5 degrees. So that was something to consider. And then we also looked at what if we changed up our pressure plate on this curtain wall and went away from a standard aluminum, and how that might impact it. And we looked at PVC or polyamide. And what we found is that we could get some more, anywhere from a 2 to almost a 6 degree. So these are some things that, just using the thermal conductivity of materials and thinking about that in context of how we're going to improve. Now, there certainly is also other things with this as far as where we could place that curtain wall within this opening, aligning the thermal insulation planes for the thermal break in the curtain wall, looking at argon, krypton, other things within the glass itself. But certainly a lot of different avenues and different ways to try to improve with making just little changes. So just a quick takeaway here on our heat energy movement. We're using the insulation to reduce that transfer. We've got to take into effect the conductivity of the materials. We've got to take into effect the placement and the continuity. And it's not always just the amount of insulation that we have, it's where we have it and how continuous it is as far as getting more efficient designs. So with that, we're going to move into air movement. And similar to what we did for heat, we'll talk about a few general principles and then get into some case studies. So air is going to go from a higher to lower pressure, and it's going to be affected by several things. Wind effects, whether you've got wind on the windward side of a building or the leeward side. You've got internal pressures that can build up. You've got the mechanical pressurizations, right? Certainly, if you can, it'd be great to always have your building operating in a positive pressure. But we know these are hospitals. We know we have infection control. We know we're in the middle of a pandemic, and there's been a lot of switchover. And how can I get negative pressurization within some of these areas in order to kind of contain those kind of situations? And so now we've got other things that we have to be concerned about as far as, are we drawing in exterior air? Are we in a warm, humid climate where we're going negative and all of a sudden we're bringing in a lot of hot, humid air into the rooms? And so what we have to look at is the air the air component of this and the air barrier as far as managing and controlling that. And so we'll talk about that in some greater detail. And just another thing I just want to mention as well is the stack effect. Depending on the height of your hospital, that can also be certainly a condition that has to be accounted for. If anyone's tried to get into the base of a building, a tall building during wintertime conditions, and you try to open the door and you can't even get the door open because of such negative pressure because of the stack effect, and that's why revolving doors are so common in these taller buildings. And the reverse would be true in the summertime with the pressure being higher at the base. So other air barrier requirements, the codes and the energy codes are going to put out things based on materials and assemblies, whole buildings. But what I want to really just kind of focus is just the continuity and just kind of how all these are going to have to work together between systems in order to try to stop that airflow. And we need it to be we need to worry about the penetrations and the punctures and structural support, in order to provide that continuity. And so a couple photos here on the right, we've got some flat wall surfaces, maybe a few tie-ins with flashings, and those are fairly standard and straightforward details that can be done. But then we get into real life, right? And real life isn't that easy. And we've got all sorts of angles, and we've got soffits and intersecting fascias and curtain wall systems. And so now we have to start to think about, all right, do I have enough bond surface to get this membrane to bond to that? Do I have the right laps? Do I have continuity between all these different planes? Does the plane change? Preformed silicones, are those going to be an appropriate type material? So what kind of surfaces do we have? What kind of compatibilities between? And are we thinking in 3D in order to solve these issues and really cut off any kind of airflow? A little mini case study here showing a situation where we did have some penetrations and breaches in the air barrier that caused some problems. And this hospital was reporting some leakage at the top floor below a roof area that had parapets, and the leakage was reported in the wintertime. And through some investigation, we looked into what was going on with those parapets, because as you can see here, as those copings were removed, you can see it's a single ply membrane, and that membrane is not well tied into the exterior enclosure, the precast. It's a brick face precast concrete panel here, and you can see the frost and the snow buildup within that. So here's a look at what that wall section looks like, and we were positively pressurized, so we had some airflow going up. And even though there was a smoke seal in it present, as well as some spray foam insulation, there were gaps and discontinuities, as well as where this parapet interfaced some taller walls, other avenues for air to get in. And so as that air goes up, we've got this convection moving moist air past these surfaces that up in the upper portions of the parapet that are very cold, and those start to create condensation. And you can see some more photos here, the condensation up at that first area where we're not tied in at the roof level, allowing that air to escape. Then you can see the frost buildup on the back surfaces of the precast, which also happened on the back surfaces of the fiberglass matte gypsum sheathing to the interior side of the roof. And then finally, you can see here the spray foam insulation with its shrinkage that occurred and provided a gap for the airflow to reach the parapet. But I also said there was other situations that were occurring in a high roof, low parapet situation, such as this. You can see in the red on the left photo where the actual joint to that parapet is located. And so the second and third photos are from within the parapet itself, looking at that panel, and you can see that there's a gap there, there's a breach. And so air can flow into that parapet and cause condensation. It can cause moisture development, wetting of the moisture sensitive material, such as the gypsum sheathing, causing organic growth and other problems. Sequencing can be a big issue too. Another hospital condition here where a curtain wall was put up and then a metal panel system was put up adjacent to it. The problem is that metal panel system was put up before the primary air seal was installed. That air seal was supposed to be on the shoulder of the curtain wall and go to the air barrier on the adjoining concrete wall, but it wasn't installed. So during spring, summer, and fall, things worked out fine. The metal panel system did an adequate job as a barrier in stopping moisture from rainwater getting in. But once wintertime came, the infiltration, exfiltration, the communication of that interior and exterior air, and the heat loss really lowered the surface temperatures on this adjoining curtain wall, and condensation began to form, such that we got down even to low enough to freeze, and you can see some of the ice buildup on the adjoining gypsum sheathing there. But it's not just these newer buildings, and not just necessarily infiltration, exfiltration through a full wall section. Airflow, even within the wall assembly itself, can cause a problem. This is a 1980s vintage building where we had precast concrete, fiberglass insulation with an FSK facer. And as you can see, the thermal barrier here juts in and goes around some of the structure. So we've got some penetrations, we've got some other things to worry about. And as you look at the photos here on the back side of that, within the soffit, you can see that the FSK is discontinuous. Certainly we don't have any taping here, and we have all sorts of breaches. So the insulation is providing some thermal buffering to the back of that precast, but it's not stopping the air. As you can see here with our temperature infrared gun, we can measure it, and you can start to see some of the moisture content that in these next photos. You can see our water indicating paper there. With the insulation moved away, you can see the sweating and even ice formations that are there. So what did designers do? They kind of knew this was a problem and seen it before, so they thought, well, we're going to come up with a system to capture and collect that condensation. And they came up with a Wept gutter system. And what it included was a precast concrete skin with two-stage sealant joints, but then they said, okay, we're going to throw this internal gutter that we've got shown here in orange, and we're going to weep that, and so when that condensation occurs, we'll get it back out. Problem is there's several issues with this, and this is a definite no-no, and it's going to probably cause you a great harm and damage to your enclosure system. A couple photos just to show you an idea of what we're talking about here. The weeps through the precast panel. You can also have the weeps at the panel joint. Those weeps alone do not mean that you have this system, but the difference is that here you can see that photo to the top right, where we cut the sealant away. It's the weep that goes all the way through both your primary and secondary, and that's going back into that gutter system. That's the concern, because now we're through our air barrier. And the photo there at the bottom just showing the air gap between the insulation, the rigid, then you've got the bad insulation with an FSK facer inboard of that. So what happens? Well, we've got issues with the weeps, as I said, creating communication of interior and exterior air. So instead of having our primary air seal at that inner line of the sealant joint, now it's all the way pushed back to where the FSK facer. And the FSK can serve as a good vapor retarder, but as an air barrier, not so much. There's going to be relaxation, there's going to be wrinkles, there's going to be areas where it's going to have to try to tie in with fireproof members and other kind of penetrations where it just isn't going to stand up, and we're going to get air movement that's going to go into the wall system. And so now we've got cold precast and warm humidified air. So now we've got to create convection within that wall cavity. And so we're really pumping in a lot of moisture, and the condensation occurs. And that condensation may or may not make it down to the gutter system. The gutter system itself may or may not be continuous and be able to get that water out. And so what we see is lots of condensation buildup. We see the organic growth, and we see the damage at the adjacent areas. So what can be done? Not an easy fix, but there are ways, to address this. Certainly stopping that airflow and getting that getting continuity back to your primary air seal, which is your sealant joints at the precast, and then putting in a spray foam insulation to the inside face. Could be an interior repair approach. Obviously not really desired in an occupied hospital, but sometimes they have to go to that route. Another option might be going with a continuous insulation system on the outside, just to keep those temperatures up above dew point with a eave system or some other continuous insulation. Or if you're considering a new building, you can look at a precast sandwich panel in order to provide that continuity. Not just the walls, though, that we have to worry about. We've got to worry about roofs. Here was a situation with single-ply membrane going on, and vapor retarder was going to be tied in on the original detail to the flange of the drain. A change was made to provide some additional insulation. The thought was, hey, let's get some better continuity around these drains, and that's an okay thought. The issue was, though, is that we no longer had that tie-in to our drain, and the vapor retarder stopped. And so what happens is we get a chance for airflow to come up underneath that roof, hitting the cold surfaces, talking wintertime condensation again, cold surface is the underside of that membrane, and now what do we get? We get moisture forming there and collecting. Photo here of a thermal infrared image shows you just that heat loss around the drains and then extending into the roofs from these breaches. And we got a couple photos there of inspection openings where some of that, where that airflow was occurring. And so on this particular one, they also were experiencing organic growth because of that moisture, as you can see here in some of these demolition areas, and then also just general deterioration. There was a coverboard, a gypsum-based coverboard that was deteriorating from those high levels of moisture. That eventually will lead to the bonding of the roof membrane itself, and we've seen in some areas just blow-offs or even inflating of that membrane due to advanced condensation issues related to this condition. So what do we do? Well, in this particular one, we look to stop the airflow, right? We wanted to keep that air from coming up into our system itself. We wanted to eliminate the potential for condensation around the drain bowl itself. And so we put in a spray foam that was then cut to fit around the drain, and then we gift wrap basically. So in this case, the vapor retarder is serving as an air barrier and tying into the drain. And eventually, this photo is before the roof insulation and membrane go back on, but you can see the effect of just being able to cut off that airflow. So some of our takeaways here, just to remember that air can transport a lot of moisture, especially in hospitals where we've got humidified air. Discontinuities and just kind of the, Bruce had said continuity is the word we want to focus. Here we had a bunch of discontinuities, and it causes a lot of problems. And then think about in designs or repairs, avoid systems that are going to rely on weeping of your primary air seal in order to drain out water from some sort of gutter or other kind of system. Finally, we're going to talk about moisture movement. And I was looking at this as from a healthcare standpoint. I said, what's different about hospitals? I mean, all buildings have moisture problems, and what can I focus and what can I talk about? And I thought, there's three things in life that you can count on. There's going to be death. We're all going to die. We certainly are all going to have to pay our taxes. And then the third thing would be hospital expansion. That's just about a given there for everyone. And so when we think about hospital expansion, we think about how do we tie in the air, water, all the other layers, and are they done, and are they done well? Here's an example of one building where we had a storefront system with metal panel, and they added a one-story addition that tied into it, and they added a little curve and got a nice seal around the precast, got a nice seal around the storefront, and thought, okay, we've stopped the water, we're watertight, and we're good to go. But nobody told the storefront that the addition had happened, and the storefront wanted to still behave the way it normally behaves, right? The storefront takes on water and it deflects a lot of that water, but some water gets past the gasket, so it'll get into the drainage cavity, and then it'll flow down within the mullions and down to a subsill, and it'll weep out. In this case now, as you can see here in red on that top right photo, our storefront continues now down below where the roof area is. And so when that water gets in, it drains down below, and sure enough, drains down into the interior. So what could we do? We could come up with a barrier system, but based on the age and the condition of that storefront, the hospital elected just to go with a new system. So we ended up putting in a new curtain wall system. We created a knee wall, and that had to be a structural knee wall because we no longer had the window going all the way down to the deck. So we had a little bit of a hinge point there. So we had to support that base sill condition for lateral loading. But then we also added in the sheathing, spray foam insulation, along with the liquid applied air moisture barrier that was all tied in order to get everything working together. How about let's look in plan at another addition situation here. And this building here is a brick clad building, brick backup, air moisture barrier. And so when it rains, that water goes through the brick masonry, collected by the moisture barrier down to the flashing, and then would weep back out. When an addition occurs, and the addition's at the bottom of this photo here on the right, the designers put in a new system. They've got a nice air-water barrier. They've got some continuous insulation. They're thinking about all the heat, air, and water in this area and thinking that they're good. But what happens when it rains on the original building? That water's still going to go through the wall And now it can still run lateral, right? We can have communication of our cavity air from outside to inside, and we can also get lateral flow of that moisture. And so, oops, all of a sudden we got airflow and we got potential water drainage into the original building. So what needed to happen is we need to think about these buildings together and where that line of defense is. And we need to have a cavity seal. We need to have more thermal continuity across that in order to tie those two together. Here's an example of a hospital building where we did just that. So we had two different cladding systems coming together. We had some breaches in areas for air and moisture to go. And so we came up with a cavity wall. This one was this was a combination of preformed silicone with a peel and stick membrane flashing, and we tied it in at each floor level with the shelf angle supports, and then this went up and around, and it also needed to continue across the roof area too. So now we can't have flow of air or water. It's captured, collected, and then drained back out. The last one I'm going to give you today is an example, again, where we've got a drainage system, we've got a drainage wall, brick masonry, and we've got a one-story addition. Very common to see a one-story addition kind of butting into another building on a hospital campus. This is a single-ply membrane, and it was tied in with a termination bar, but surface applied. So again, similar to some of the other examples we had, when the water comes, wind-driven rain against that wall, that water is going to go into the masonry cavity, and where's it going to go? It's not going to be stopped by that surface applied seal from the roof. It's going to keep on going down within the cavity, get down to either the base of the wall or there's some intermediate flashing that was in the wall before and drain out. And sure enough, that's what's happening. So we've got a new addition here, and there are signs of water stains in the suspended ceiling that's just below this area. Further looking, open up those ceiling tiles, you can see the moisture staining that's coming down the face of the brick masonry. Now this is the same masonry wall that you're seeing here above, but now it's down below within the wall assembly. And so there you can see the water draining out and not being collected properly. So what can we do? We can add in a through wall flashing, right? This isn't rocket science. We just need to think about these things ahead of time and plan for them. So we need to get that water out of the wall with a flashing. We like to use a two-piece flashing so that future maintenance, replacement, or repairs can be done to the roof without the need to do future repairs then to the brick. We don't want to have to tear out something that was new just to get and be able to do some maintenance. So the keys there are just having a nice pan flashing. This is tied into a membrane and a good termination. It can either be terminated in a reglet or a term bar and have support to get some positive pitch, have that wept out and provide continuity. So again, now we go from a drainage system to a barrier system, but we've got continuity and ability to get that water out. So with that, I'm going to, I've got takeaways, I'm sorry, before I turn it over to Bruce. So we know that moisture is common in all the buildings, but we know that we've got a lot more additions going on, a lot more interfaces and conditions that are going to happen at these healthcare facilities. So those are the keys. And we got to think about, okay, how are we going to get that from a drainage to a barrier or barrier to a barrier and just all those interfaces, and whether that's cavity seals, end dams, or other different things in our toolbox in order to make those transitions. And with that, I'm going to turn it over to Bruce so we can talk about some items to maybe think about before you get into these problems and how to avoid them altogether.
Thanks, Kevin. So yes, as Kevin said, we spent some time now talking about heat, air, and moisture and the problems that they can create, and sometimes how we need to solve those problems that have been created in healthcare facilities. But clearly we want to do more than that. We want to be able to be there in a way and a capacity for you that allows you to not have these problems in the first place. So clearly the key is to be proactive, is to be ahead of the curve, is to be thinking about what could be coming down the road, trying to solve problems before they become manifest. Clearly, we get that the risks for you of problems in healthcare facilities is very high, and we want to make sure we help you mitigate those as much as possible. Commissioning is a term that you probably have heard. Certainly, it's been around for a long time. Mechanical, electrical, plumbing. Commissioning has been de rigueur for a long time. The that is largely a work that is done during design, but then heavily after the building is built with testing and balancing of all of the systems inside your building. Well, that is not really the same way we can commission the enclosure. By the time the enclosure is done, the issues are all locked in. We need to be there earlier and really be in front of a lot of the both design and construction issues. We're probably walking out of our commissioning job before the MEP commissioning agent is probably even significantly engaged on the building site. So the question is, will it work? In design, you have some interesting products, some interesting concepts, some very beautiful aesthetics that the architect desires. And clearly, you've got a job to make sure that you can build it and that you'll be happy with it after the fact. Buildings are getting more complex, especially healthcare buildings. And all of that requires more attention during design, into construction, and the stage between those two, which we like to do, which is a series of testing mock-ups of the design concepts. And obviously, as we go out on and build these buildings, we're checking that there's quality in their construction. So, as I've said, it's really a process that the earlier you can start with it, the better you'll be for it. We've been involved with projects where we've been told, oh, by the way, we're halfway through construction. We'd like to get you on board. And it's kind of late at that point. If you can get us on board when it's in schematic design, that's great. In the design development is okay. In construction documents is a little after we're happy, but certainly by the time construction starts, it's kind of late. And there's diminishing returns. And of course, if we find something early on, it just requires some redrafting to mitigate it. If we find it later on, it could be a significant cost to solve. So what do we do early on? We obviously start when the architect is preparing his drawings. We'll give a critique of that, a peer review. But then once it gets into either if there's a design assist process and the enclosure contractor is on board, certainly they'll be preparing drawings that will be interested in those details. We like to mark up a lot of shop drawing details and really work out consideration of a lot of how the issues that Kevin just discussed about how heat, air, and moisture are mitigated by these designs. And then, as I said, really one of the areas where we really like to roll up our sleeves is in mock-up testing. So mock-up testing is not done on all buildings, and certainly it's oftentimes considered too expensive. We see that typical mock-ups can sometimes be in the order of $50,000 to $100,000 or even more. But we believe that the money spent on those type of projects is really well spent because we realize that healthcare facilities are mission-critical facilities, and that if we can learn how the facades and enclosures are going to work in the earlier stages, if we can make sure that their systems are all working together, we're going to learn a lot. So mock-ups are full-size specimens. They're built from the processes and products that are going to be used on the project. You try and recreate as much of it as possible. Sometimes they get a little exotic because there's little pieces and parts of different elements that the architect has designed. And they're tested in some controlled environment. Usually it's in a laboratory. There's special labs that are designed for testing mock-ups. Sometimes they're done on the project sites, and then they have to be adapted to be able to be tested at the project site. But they require, at a laboratory, they're going to be built against what's called a strong back wall. That wall is going to allow you to pressurize between the specimen, the test specimen, which is your sample of the wall, and the strong back. It's going to allow you to test the wall under air leak conditions and water testing conditions where the air pressure is a simulates the wind loads that are going to be occurring on the building. And then it even allows you to check structural loading of the cladding to make sure that under the full design wind loads, the cladding is structurally behaving the way it is supposed to. So they're very rigorous tests, but once you've gone through them, you have a lot of confidence that the design is really going to be working out well for you and in building your building. Another thing that we're getting more and more into these days is thermal testing of mock-ups. It wasn't really something that was on the boards early in mock-up testing, but as buildings' thermal performance becomes more critical, we're doing more of the testing under the AMA 501.2 type of test criteria that allow us to see how walls are going to behave under critical thermal conditions. And really what we're looking for is either pass-fail with values such as condensation resistance factors or the U value of the walls, but we're also looking for qualitative results such as some of the cold spots that Kevin had shown with thermography on the building. We're trying to make sure that in the mock-up stage we're going to be catching those kind of things, and we're going to be making sure that they don't carry through to the built construction. So if you successfully pass, or you ultimately will successfully pass your mock-up phase, and you'll go on to building your building. At that time, we're really concerned about the construction of the quality of the contractor's work. A lot of this work is not done on project sites. All portions of buildings these days have a high degree of prefabrication. We're getting products from North and South America, from Asia, from Europe. All of these things have fabricated somewhere in a shop. We need to be able to make sure that the quality that's being done in those off-site locations is what was expected and what was going to be brought in fabricated units to the building. Once they're fabricated, it's very difficult to determine that they were actually built because it's all kind of buried inside this fabricated unit. Then they will come to the building, and then we have the opportunity to really inspect them once they're coming together. The pieces and parts are coming together. We'll make periodic site observations. We'll be looking for visible conditions that are visible to us to see at the time of our inspections, and we certainly will be documenting what we find. One of the important things is if we see it, we've got to tell somebody we saw it so that the proper construction team can start to do something about it. So we will be looking very closely at the details. I think WJE has a reputation for having their nose always in the minutia of the wall systems. We like to dig in. We like to look underneath the flashing and see that the brick masonry underneath it is where it's supposed to be, or that flashing over on the left certainly deserves a drip edge. We will get as close as we can with proper PPE so that we're working safely. And we'll really want to see all the details of the wall. We also would like to make sure that we're going through it with the tradespeople, where we get the opportunity to sit down and talk to them or stand up and talk to them, point out what we see, get them to say, nod their head affirmatively or disagree with us if they think they've got a different approach to what we have. We're definitely not the only people here who got interest in the quality of the project. Since we believe, well, we like to say that we've been involved since the design and shop drawing phase, we obviously will be very familiar with the design and the shop drawing details of the building. This will be a great opportunity for us to compare and contrast what we're seeing as the wall's built with those design details. Here we've got an issue where we've got a transition membrane between an air barrier and a curtain wall. And the transition membrane had some issues with being able to be flexible enough to be bent into the right position. We had to do some extraordinary care in the construction of those membranes to make sure that we were going to get the continuity that was so important to the air, water, and vapor barriers. Sometimes we find that things just weren't designed the way we think they should have been. We can find that there's a flashing that was built according to the drawings, but it leaves a hole It was allowing water to just drain off the end, and we came up with a way to transition that to the curtain wall while it was still being built, obviously solving a problem before it became manifest in the building. We do a fair amount of this testing during the construction phase. If you looked at these marked up drawings of the elevations and the roofs, you could see that we're being pretty extensive. We want to do a lot of water and air testing on the wall. Now, these are different tests than in the mock-up. These are more quality assurance or quality control testing at this stage, because we want to make sure that what they've already done has been vetted and that the final construction has worked it all out. We will be using a handheld water spray devices. It's very common to want to go up and test with a simple spray nozzle. This is a certified test by AMA 501.2. What's good about it being a certified calibrated test is it can be repeated. So if you don't pass the first time, you can make a repair and you have the opportunity to go back and repeat with the same conditions and prove out that you've solved the problem later on. There's other test methods that we can do as well. There's the spray rack, which obviously covers a lot more wall area than just a nozzle does. And then lately we've been using a lot of large fans to create dynamic wind conditions to be able to recreate the wind on the facade itself. These are some other testing. Sometimes air barriers deserve to be tested early during construction with devices such as the bubble gun that's in the upper left. Those are techniques for just making sure that there isn't any defects in small localized areas of the membrane. We can do pull testing to verify that the membrane is adhering to the substrate, and we can do full chamber testing to verify air leakage through the membrane. Since we're working on the building doing these testing, access is a challenge. We have to get lifts that get us high up on the wall. On the inside, we have to be able to build chambers to get air pressure differences. We have to work around, obviously, ongoing construction of interiors to make sure that we can get this testing done in a timely manner before they start to build out the inside of the building. Roof testing is also critical. We can do a number of different types of tests of the roof to verify that it's going to be leak-free. On the left is a couple non-destructive tests. One is a Tramex roof and wall scanner in the left portion of that photo, which tests by electrical fields that are created by within the roof membrane to look for impedance, which would be an indication of the possibility of something conducting electricity, which would probably be moisture. The other one is high voltage testing, which is done where if there is a breach in a single ply membrane, a PVC type of membrane where it's a thermal or it's an electrical isolator, the breach will show up with conductivity through that hole. We can find holes in the membrane. We could solve those holes before the roofing is completed and may be covered up. Flood testing is a common test method. You block the drains. You stand a head of water on the roof for 24 hours. You make sure that there's no leaks below. Thermography, as Kevin showed on the walls, can also be applicable to doing on roofs, looking for wet insulation, possibly already wetted by maybe sometimes we find it's installed before the finished roofing is installed. Maybe there was just a temp roof. A lot of times insulation could be damaged during construction. One test that we're doing more of is whole building air testing. Now this one has to be done after the whole enclosure is done, potentially even the whole building is built. And it's a great test to give you final results on your building's air tightness. unfortunately, it's done kind of late if you want to learn lessons and solve problems, because you've got a whole building now built, and it's tough to go back after the fact and solve problems. But hopefully what we do with whole building air testing is prove out that the QA/QC steps we've taken during commissioning have manifest themselves with a good airtight building. So in regards to commissioning, what I'd like to take away is that the earlier you can start the process, the better you're going to be for it. That it's a hands-on, commissioning is a hands-on process. You have to really dig into the building and understand the construction, watch it while it's being built. And there's quite a few quality assurance tests that are available to us to verify enclosure performance. So with that, we are done, and we have a few minutes left. Kevin and I thank you for your time, and we have some time, I think, to entertain some questions.
All right, thank you, Kevin. Thank you, Bruce. As a reminder, if you have a question, please type it into the Q&A box and hit submit. And if we don't get to your question during the call today, we will follow up with you afterward. All right, let's take our first question. For continuous insulation without bats in the stud cavity, what is the recommended R value of the board insulation in your THERM model?
Okay, I will, I'm going to slide us back to that slide that we're talking about here. Let's see, there we go. So as far as the recommended insulation thickness, it's going to be very dependent on, what is the design criteria that you're designing to. What is the code requirement? And now the code's going to have prescriptive, but there's also going to be performance-based. But if we're just talking about prescriptive, they're usually going to look, as you're looking in those tables, you're going to see a continuous insulation and a cavity insulation component. But what you also have is the option to do a U-factor alternate, which would be taking the entire assembly of the wall. So the biggest component for your thermal performance would be the insulation. But by doing a U-factor alternate, you can look at, for your insulation, let's just say we've got a 2 inches of rigid extruded polystyrene at R5 an inch. So now we take that 10 inches R value, and from the U factor, we're looking at our, the inverse of that R. But we'd also be looking at the sum total of the inverse of the R of the rest of the assembly. And so we have air films, and we have even the little bit of benefit we get from different sheathings and other kind of materials. We can add up all those together in order to kind of fully get the most efficient design and still being within code requirements. So if the question is related to, what does that need to be in order to get me my sheathing temperature at such and such, for this model, I believe we did use 2 inches on this particular one, but what would really be needed is going to be more of a factor of what's driven by code design, and then also you may want to look at what your interior conditions are and your relative humidities and where you might need to be from a standpoint of condensation. I would say if you're going fully continuous insulation, it's going to be the energy code that's going to drive the response, because your interior face of your sheathing is going to be very close to the temperature of the interior conditions, at least close enough that you're not going to be near dew point. If you're in a hybrid situation, then you really have to start looking at, what from a condensation standpoint, because you're going to have that bad insulation buffering the interior surface of your sheathing to a point where you may approach dew point level. So hopefully that answers the question.
Okay, thanks, Kevin. The next question, Kevin presented about airflow through a roof assembly. He said that this resulted in water leaks. Can he explain how the airflow caused water leaks?
Sure. Yeah. Let me pull up the slide for that one as well. One second here. Oops, I think I grabbed the wrong one. Bruce, can you grab the slide for that? So as far as the water leakage that occurred, we had a positively pressurized hospital And we had avenues for that air to get up into the roof assembly, not only from the roof drains, but from some other penetrations through the roof. And then compounding that problem was that we did have some breaches in our air barrier along the perimeter of the roof. So if you can think about the airflow going up into the roof and basically traveling beneath the roof, and creating some more kind of convection and movement loops, air transporting that moisture. And then if you're thinking about a wintertime condition where we have cold outside temperatures, and we also have some, especially on days when we've got the cloudless skies, we've got nighttime radiation. So those temperatures on those membranes, especially the white membranes, now with the new energy codes are not so new anymore, but the white of the roofs, the lower the temperatures on those membranes can get. And that's both surface temperature on the top, but also there's not much R value to that membrane either. So it's the underside of that as well. And so we've got warm, humid air hitting the underside of that membrane, which is below dew point, or even hitting the cover board, which potentially could be below dew point as well, and then forming droplets. So it starts out as a condensation. If it's cold enough, it frosts, and then as it gets a little bit warmer in the day or the sun comes out a little bit later, then that turns into a liquid form. You get enough cycles of that, it starts to build up, absorb into the materials, and you start to get saturation and deterioration, eventually puddling enough around those that you can start to get leakage then into the interior of the building, back down through the same avenue where the air went upward.
Okay, our next question. With the various roof testing methods, which is most preferred? Second preferred and least preferred?
Okay, I'll take that one. Clearly they probably depend a lot on the type of roofing that you're dealing with. So for instance, we do like the high voltage testing, but there's certain roofs that you cannot use that on. For instance, EPDM roofs are not possible to get the isolation that you need, the electrical isolation you need with the membrane, to be able to find those leaks. So clearly you have to know your roofing membrane in order to pick the right test. The flood testing is very good, but sometimes it's difficult to do, especially in buildings that are not yet completely enclosed below, and the roof is being built in pieces and parts. You might have to be building a lot of dams around the perimeter to contain the water. We probably, obviously, inspections, I go without saying, inspecting the roofing as it's going down is a key way of probably the first and foremost before you even do any testing. So clearly, like the other types of tests, you have to pick your test depending on the type of circumstances that you're going to have, the type of roofing membrane, and how the roofing is being done and the timing for it.
Okay. Thanks, Bruce. We've got time for one more question. How do you install the through wall flashing through existing wall? And this person's referring to the slide preceding the commissioning slide.
Okay. Sure, I can take that. The through wall flashing, because you have to remove masonry and sometimes several courses of masonry in order to get that through wall flashing in place. Bring that one up. There's different options for that, kind of depending on what your building is. If you've got a concrete frame building, it's pretty easy. They can drill in and they'll put in stainless steel dowel pins, probably about anywhere from 16 to 24 inches on center, and you get some arching between those brick units so that you can just put in a line of those. They can demo below it. You can build the brick back in, let the mortar set up in between the pins, and then remove the pins or cut the pins. If you're in a situation where you're looking at steel stud or something that doesn't have quite the robustness to provide that, you can do it in several different ways. Kind of a little clever, ingenious way the contractors will sometimes use is if it's a taller building and you've got a shelf angle above, they'll put down and actually grab the shelf angle from the level above and use basically a support to kind of I'm trying to think of the best word, but basically come underneath and provide support to the masonry below by hanging it from the shelf angle above, and that allows you again to then demo below that, and then you can build it back in kind of a fashion where you get it to set up, and then you can take out the support points individually. If you're out of chances from those, you don't have any real support points, then you're looking at taking smaller kind of pyramidal sections out at a time. That's not ideal because you're gonna have a lot of splice points, but in a worst case scenario, can always be done that way.
All right. Again, thank you, Kevin, and thank you, Bruce, and thank you all for joining us today. We hope it's been educational. As a reminder, you will receive an email this afternoon with a link to an on-demand version of this webinar that you can use to rewatch the presentation at your convenience or to share with any of your colleagues who weren't able to join us today. And that webinar will also have a link to access related resources, including a PDF copy of today's presentation. It will also include a link to download your certificate of participation. If you have any questions about the topics that were covered today, please don't hesitate to reach out to Bruce or to Kevin. And if you have any questions about this webinar, please reach out to me, Liz Pemper, at lpemper@wje.com. So again, thank you so much for your time, and we hope you have a great rest of the day.